What is going on, everyone? Welcome back to another video. This is going to be part one of the first mini-series on this channel, where we are going to be doing the Converging Diverging Nozzle study in ANSYS Fluent. I will show you guys the parameters that I have chosen to build this analysis, and I will cover a little bit of calculations in order to determine what our boundary conditions are going to be for the various types of flow and flow events we want to occur in our nozzle. So let's jump right into it. The flow through a converging diverging nozzle is a very interesting study to do, as it allows us to study many different flow regimes, as well as events that may occur within the nozzle depending on what the boundary conditions of our nozzle are. The two conditions of the converging diverging nozzle that are studied are the subsonic choked flow and the supersonic flow conditions. The subsonic choked flow regime is denoted by the top portion of this graph here in figure 13.12 that I got from Fox's and McDonald's Introduction to Fluid Mechanics. So although the velocity of your flow through the converging part of the nozzle increases as your pressure decreases, due to the too high of a pressure at the outlet, the flow never reaches Mach 1 or sonic flow by the throat of the nozzle or the critical area. Now, this is important because once the flow becomes sonic at the throat, it's able to continue to accelerate supersonically through the diverging part of the nozzle. Now, beyond the flow conditions that are studied in the converging diverging nozzle, there are also flow events that will affect the flow in and around the nozzle. These include normal shocks, oblique shocks, and expansion waves. However, more on those later. In this video, we're going to focus on the subsonic choked flow condition. In order to set up this analysis in ANSYS Fluent, I've gone ahead and chosen some parameters for the geometry and inlet boundary conditions. And therefore, using area and pressure ratios, we will be able to determine what our outlet pressure is going to be in order for our flow to remain subsonic throughout the nozzle, hence the subsonic flow conditions. So let's jump right into those calculations. So in order to start the calculations, let's start by writing down all of the information that we know. So here I have my converging diverging nozzle. And I know some information about its geometry. I know that its half height at the inlet is 250 millimeters. And its half height at the outlet is 290 millimeters. Now, the reason why I'm saying half height is because in ANSYS, we are going to be simulating simply half the nozzle. I've also chosen other inlet conditions, such as the inlet Mach number to be 0.5, the inlet static pressure to be 225 kilopascals, and our static inlet temperature at 293 Kelvin. So the first information that we would need to find in order to build our nozzle the most efficiently is our critical area, otherwise known as our throat area, A star. Though the throat area can easily be found by evaluating the area ratio AI over A star at our inlet Mach number of 0.5. Now, if I go to the isentropic flow tables, I get this area ratio to be approximately equal to 1.34. Now, in ANSYS Fluent, we will consider our converging diverging nozzle to be planar, meaning it will have a cross-sectional area of a rectangle. However, I will show you guys how this makes the calculations easier because the area ratio will become a function of our heights of 250 and 290 at the inlet and outlet respectively. So if we assume the cross-sectional area of a rectangle, and we assume that it has a width of 1, and obviously the height, or the half height, I should say, of 250 millimeters, well, the inlet area then becomes BI times 2HI. Similarly, if I take the cross-sectional area at the throat as a rectangle and assume that the width of the nozzle is constant throughout its length, therefore the width of the nozzle at the throat is also equal to 1, well, I can write the area at the throat to be equal to B star times 2H star. And so if I evaluate the area ratio from before, AI over A star is equal to BI to HI over B star times 2H star. I know that my width is constant throughout the nozzle. Therefore, the area ratio is simply a function of the half heights of our nozzle. Knowing that the area ratio was found from our isentropic flow tables at 1.34, based on the Mach number of 0.5, we therefore can find our critical height of our nozzle. Which is approximately equal to 186.5 millimeters. So there you have it. We have found the half height at the critical area of the nozzle to be equal to 186.5. So now we have all of the critical information in order to build the geometry of our nozzle in ANSYS Fluent. Now let's go ahead and find the exit pressure that is going to determine our flow to be subsonic. So in order to find this pressure, the first thing that we're going to have to do is to find the total pressure at the inlet, which can easily be found through the pressure ratio PI over POI evaluated at our inlet Mach number of 0.5. From the isentropic flow tables, we get this pressure ratio to be approximately 0.843. Therefore, if we plug in our inlet static pressure of 225 kilopascals, we get our total inlet pressure to be equal to 266,000 904 pascals. Similarly, we can do the same thing to find the total inlet temperature. Now, in order to find the pressure at the exit of the nozzle that is going to give our subsonic condition, we need to find the pressure ratio, PE over POE, evaluated at the area ratio, AE over A star, which, as we saw before, for a planar nozzle that has a width of 1, the area ratio is simply a ratio of the half heights of our nozzle. We already knew our outlet half height to be 290 millimeters. And we just recently found our throat half height to be 186.5 millimeters. Therefore, the exit area to throat area ratio can be found to be 1.555. And if we go ahead and plug this into the isentropic flow table for a subsonic flow condition, we get our pressure ratio, P exit over P total exit, to be equal to 0.890. Knowing that for isentropic flow, the total pressures throughout the nozzles are equal, we can find the static exit pressure to be equal to the pressure ratio previously found at 0.890 multiplied by the total pressure we found earlier of 266,904 pascals, giving an exit pressure of 237,544.56 pascals. And those are the calculations needed in order to determine the subsonic flow conditions. So now let's jump over to Ansys Workbench in order to build this analysis in Fluent. So now that we are in Workbench, we can go ahead and start building our simulation. First things first is to grab the Fluid Flow Fluent analysis system and drag that into our project schematic. And like any simulation, the first thing to do is to build the geometry. So I'm going to double click on geometry and launch SpaceClaim. As you can see down here, it says starting SpaceClaim. So I'll wait for that to load. Now with SpaceClaim open, we can go ahead and start building our geometry. Since this is a CFD simulation, the geometry that we're going to build is going to reflect the fluid domain of the converging diverging nozzle. So first things first, I'm going to end sketch editing up here, press the check mark, because that by default, SpaceClaim has this editing on the ZX plane. I want to build my geometry on the XY plane because it's going to be easier for initialization in Fluent. So I'm going to go ahead and end sketch editing. And I'm going to re-enter sketch mode by pressing on the pencil crayon called sketch mode. And I'm going to hover over the XY plane. So I'm going to select it, make this flat. And now we can start building our geometry. So the first thing that I'm going to do is grab the line command. And then from the origin, I'm going to draw a line upwards. And I'm going to press escape. And I'm going to come ahead and press the dimensioning tool and dimension this line to be 250 millimeters, otherwise known as my inlet. There we have it. Now I'm going to choose the line command again, and I'm going to come down here back to the origin, but this time I'm going to draw a line horizontally. Press escape again, and I'm going to take my dimensioning tool, and I'm going to dimension this line to be 850 millimeters, the dimension of which represents the length of our nozzle. And this line is also going to serve as the axis of symmetry, as we're only going to be simulating 1/2 of the nozzle in order to get a faster computational analysis. And I'm just going to mirror the results that we get for the half over the line of symmetry. So next up, I'm going to grab the line command again, and I'm going to draw my outlet. Draw a line vertically upwards, and I'll press escape, and I'll take the dimensioning tool again and dimension my outlet to be 290 millimeters. Now, all of these dimensions are dimensions that I've chosen to make up the shape of my nozzle. Though we are missing one critical length, which is the throat width. Now, this throat width was obtained through the pressure and area ratios that I showed earlier in the video. And this was found to be 186.5 millimeters. So how do we replicate it? Well, I'm going to go ahead and choose my point command up here, and I'm going to place a point within my geometry here. Now I'm going to take the dimensioning tool, and I'll choose the throat to be at a distance lengthwise of 350 millimeters. Again, I've chosen this dimension, but I'll dimension the actual width to be 186.5, again, which was determined through ratios. This was the only length that was not chosen. Now, with all of these dimensions initialized, it is time to build the wall of the converging diverging nozzle. And the method I'm going to show you guys is going to be a rough approximation of what the wall would actually look like, since we are limited and only have 3 of the critical lengths. So to do this, I'm going to go ahead and choose the spline command, looking like this. And I'm going to start it at my inlet, like so. I'm going to choose an arbitrary point between the inlet and the throat width. I'm going to connect it to the throat. I'm going to choose an arbitrary point between the throat width and the outlet, and I'm going to connect it to the outlet. Next, I'm going to press escape to confirm this line. Now, as you can see, this is already a fairly good approximation of what the wall would actually look like. But we can go ahead and click on the line in order to get the spline's trimming points. Now, what I'm going to do is just drag these points in a way so that I can get more uniformity in the converging and diverging part of the nozzle. Evidently, if you had more points, or if you knew more points along the nozzle wall, or if you had the actual equation of the wall, the spline representation would be more accurate since you're connecting it to more points. But for educational purposes, this is more than acceptable. So I'm going to go ahead and trim my spline a little bit to get a better uniformity in the convergence and divergence, and I will be back with you guys in a second. Welcome back, guys. I have finished trimming my spline, and I'm pretty happy with the result that I got. Again, the goal of this spline is to give an approximation of what the geometry of the nozzle wall would actually look like, since we only have so many critical lengths and we don't have, say, the actual equation of the wall. And the reason why I added the arbitrary points in between the inlet and the throat and the outlet is so that we can have more trimming options in our spline. Again, the more points you have in a spline, the more precise you can get with your geometry or the shape that it creates. But all in all, I'm pretty happy with the shape of my spline. And that's going to be it for the lines that we need to create the geometry. So in order to create this surface, we need to end the sketch editing. So I'm going to go ahead and press on the green square down here, or you can press on the check mark, either one. And as a result, our surface has been created. So now we can go ahead and move on to the mesher and start meshing our geometry. So I'm going to exit SpaceClaim by clicking on the big X at the top. And I'm going to launch the mesher by double clicking on mesh. And as you can see down here, it says starting meshing. So I'll wait for that to load. Now that we are in the mesher, we can go ahead and start building the mesh for our geometry. Now, there are many different ways that we can actually build the mesh for this model. There are ways that require us to determine the number of divisions we want along the spline and the axis of symmetry. And then based on that information, ANSYS will go ahead and create a mesh for us. Or there's ways that require us to split the surface with different lines. And we determine the number of divisions we want along each of those lines. And this could be a good method to concentrate more of the elements around the throat of the nozzle where you'll have more interesting information occurring. However, for such a simple simulation and one that does not require a lot of computational power, these mesh can take up more time and can be very hard to control. So the way that I'm going to show you guys is by far the easiest way, and we'll just go ahead and check the quality to ensure that it's going to be a good mesh for the analysis. And if the quality is poor, then we'll go ahead and adjust the mesh controls or the actual geometry that we built in SpaceClaim in order to get a better quality mesh. So the first thing that I'm going to do is generate the default mesh from ANSYS. So to do this, I'm going to right click on mesh and press on generate mesh. Now by default, the mesh is going to be very, very coarse. So we'll need to add a sizing regardless. So in order to add a sizing and to make the mesh smaller, I'm going to go ahead and right click on mesh. I'm going to insert and press on sizing. Now, as you can see down here, the yellow boxes are the information, are the minimum information that ANSYS need in order to create the sizing. So we're going to start with the geometry. We're going to choose the face selector tool up here. We're going to choose the only face we have. And I'm going to press on no selection and press apply. So now you can see that we've added one face to our geometry for our sizing. Next up, from the default mesh, we can see that the element size was given to be this. So I'm going to go ahead and change this value to make it smaller than this. And the element size that I want is going to be 0.005. Which should create fairly small elements, but not too small that we overwhelm the computational power that we need for the analysis. So with all that being said, I'm going to go ahead and update my mesh based on the sizing. And as you can see, the mesh is a lot more fine now. You can see that there are a couple elements that are a little bit skewed. So we'll go ahead and check their orthogonal quality to ensure that this is a good mesh for analysis. So to do this, I'm going to press on the plus beside quality down here, making sure that we have mesh highlighted here in our tree. And for mesh metric, I'm going to choose orthogonal quality. Now, what this is going to check for is how close each of our elements are to being a complete square. The closer they are to being completely orthogonal, and the more that we have to being completely orthogonal, the better quality our mesh is, and the better our analysis is going to be. So as you can see down here, with the orthogonal quality mesh metric, a bar graph appears, which shows the percentage of orthogonality on the bottom, and the number of elements on the y-axis. As you can see, the majority of the elements are within the top percentile of this graph. And if we go ahead and press on the actual block diagram here, it will show all of the elements within this category. If we go ahead and choose the next category, it will show all of the elements in the next category. So this is a good way of checking how skewed our elements can get in our mesh and identifying what may be problematic areas within our mesh. If we go down here to the lowest one, we can see that we only have 2 elements. And if we go ahead and check the information on the side here, we see that these 2 elements have an orthogonal quality of 75%. We can also see that the average quality of our elements is 99.7%, which is very good. So I don't expect there to be any problematic areas that will lead our analysis to diverge or give a bad result. Now, what if your quality is lower than this? Well, there are several things that you can do. The first thing that I recommend, and probably the easiest thing to do, is to adjust the element size in your meshing here. And this could either be making it bigger or smaller. It sort of just depends on how the elements stack on one another in our geometry. So by making the elements bigger, maybe they incorporate an area that would lead to a higher skewness if it was smaller, or maybe making the element smaller will fill up areas better. It can go either way. Now, if this doesn't work and you don't get a better quality this way, I do recommend editing the spline or the wall that you've created to get a better uniformity in the top of your mesh here. Because ultimately, it's the spline of this geometry that is causing this skewness in our mesh elements. Because if this was to be a perfectly square geometry, then it is safe to assume that all of your elements will be perfectly orthogonal. So these are just some tips and tricks for you guys if the quality of your mesh isn't looking too good. So now with our mesh created, we can go ahead and add some name selections as well before we move on to Fluent. Now, this is very important for Fluent because it's going to allow Fluent to more easily place its boundary conditions or know where our boundary conditions are, meaning where the inlet is, where the wall is, yes, where the outlet is, and where the line of symmetry is. So we'll go ahead and add those. To do that, I'm going to choose the edge selector tool up here, and I'm going to choose my first edge. I'm going to right click, and I'm going to press on name, create name selection, and I'm going to name this the inlet. Press OK. And it's as simple as that. So we're going to go ahead and continue this process for the other edges. So I'm going to create my outlet. I'm going to create my wall. And I'm going to create the symmetry line. And the last name selection I'm going to do is for the actual fluid flow, the area that is within the borders of these edges. So for that, I'm going to choose the face selector tool instead, and I'll press on the face, right click, create name selection, and call this fluid flow. Press OK. And if we go to the tree up here, we can press on the plus beside name selections. It lists all of the name selections that we've made. And it's always very important to verify that they're in the correct place. So we'll press on the inlet and it'll show where our inlet is. Press on the outlet and it shows where the outlet is. Press on the wall. That's where our wall is. Symmetry, symmetry, and overall fluid flow. So that is all good to go. So with our mesh created and our name selections in place, we can go ahead and move on to the actual analysis part and launch Fluent. So we'll go ahead and do that. We're going to click on the X for the mesher. Now, since I did not update the mesher after we created the name selections, they have not been set to the setup of the program, as you can tell by the lightning bolt that we have beside mesh. We want this to be a check mark before we move on to Fluent. So to do this, we're just going to right click on mesh and we're going to press on update. And this will ensure that all of the information gets sent to the setup of Fluent. Just like so. So now we can go ahead and double click on setup to launch Fluent. Now, before we get into Fluent, we're met with the Fluent launcher where we want to specify a couple things. First off, we're going to want double precision for this analysis. And for the computer that I'm running ANSYS on, I know that for better computational results, I can up the solver processes to 2 and the GPUs to 1. Now, this is pretty generic for most computers, but just verify in your system settings the parameters that you have here. So with all of this initialized, we can go ahead and press on start. Now with Fluent launch, we can go ahead and start the analysis of our converging diverging nozzle. So I'll press OK on this text here. We do not need it. The first thing that I'm going to do is double check my mesh. So I'm going to press on check here under mesh. And it's going to print various things to the screen. The thing that we're most interested in is the volume statistics here. And we just want to make sure that none of these numbers are negative, because this is going to lead to bad computational results. You cannot have a negative volume, but when there are errors that occur in the mesh, it is possible that you end up getting a negative volume. So if a negative volume appears here, you're going to want to have to adjust your mesh and your controls in the previous stage. So with that good, we'll go ahead and specify other information that we need. The first one is going to be a density-based solver. And the reason for this is because we are working with compressible flow. Therefore, the density of the fluid is going to change as we move through the nozzle. And for 2D space, you can either specify planar or axisymmetric. For this analysis, I'm going to choose planar as my 2D space. It's just going to make the analysis and the calculations easier to do. For axisymmetric, you would think the 2D plane to have a circular cross-section, but for planar, what you're doing is you're assuming this 2D plane to have a cross-sectional area of a square or rectangle. So you would think of it as a rectangular duct. And if we assume the depth or the width of our nozzle, I should say, to be 1, then the area ratio is just a function of the dimensions that we initialized in SpaceClaim of our inlet and outlet and our throat, of course. So that is all good to go. The next thing I'm going to move on to is models. So we'll double click on models. Multi-phase flow is off, so that's good. We're only working with one fluid. We're going to want to turn on the energy equations. And so by clicking on the checkbox beside energy equation, we are adding it to the Navier-Stokes equations that are used in the calculations of this analysis. And we want these energy equations because we are working with compressible flow. So once you check the box, press OK. And for viscous, this window is going to appear here, and I'm going to choose inviscid flow. So press OK. The rest of these we don't need to change. So next we can move on to materials. If we double click on materials, We can see that for fluid, by default, we have air, which is good. That's going to be the material that I'm going to use for this analysis. If we double click on air, though, it will open up this window. And by default, we see that the density is constant at 1.225 kilogram per meter cubed. Now, this is not good because we know that the fluid in the converging diverging nozzle is compressible because it's moving at such high velocities. So to simulate this, we are going to press on the drop-down menu here, and we're going to choose ideal gas instead. To confirm this change, I'm going to press on change create. And so that has confirmed the change that we made for air. Now, say if you didn't want to use air and you wanted to use a different material, to do this, you would press on the Fluent database here, and this would open up this window with all the list of fluids. And you could go ahead, say if you wanted to use acetone, you could go ahead and use this material. All of its properties are listed here. So if you wanted to, you could adjust all the parameters. If you were looking for a, say, acetone with a specific viscosity, for example. And to add it to the project, all you have to do is press on copy. And so if you go ahead and press on the, well, if you close this window, sorry, and you close this one as well, because we don't need them, you can see that acetone has been added to your fluid material tree. Now, just because it's been added here doesn't mean it's actually been initialized to the surface yet. That is going to be the next step. So to do this, we're going to press on cell zone conditions. And we're going to double click on fluid flow. So as you can see, fluid flow is initialized as air. If we didn't want air and we wanted to change this material, all you would have to do is press on the drop-down menu, and all the materials that you've added before will be listed here. So if I want acetone, I would go ahead and press on acetone, and then I would have to press apply to confirm that change. But I want air for this analysis, so I'll keep it to air. Close the window. So now it's time to look at the boundary conditions. So I'll double click on boundary conditions. And as you can see here, this is where our named selections that we made in the measure come into play. So the inlet, we can see, is defined as a velocity inlet. That is not good because we are specifying the pressure at the inlet. So I'll change the type to pressure inlet instead. And that will open up this window here. Now the supersonic initial gauge pressure, that's going to represent our static pressure, or the pressure that we have chosen at the inlet of our nozzle. So I've chosen this to be 225,000 pascals. The gauge total pressure, this is your stagnation pressure, or the pressure that is true throughout the nozzle. And this pressure is determined through the area ratios and pressure ratios of the converging diverging nozzle, the calculations of which I showed at the beginning of this video. And so we found this pressure to be 266,904. Next up, we also want to initialize the thermal conditions as well. So as you can see, the total temperature right now is 300 Kelvin, but I chose the initial temperature at the inlet to be 20 degrees Celsius or 293 Kelvin. So I'll go ahead and initialize that there. Press apply to confirm the changes, and we can close this window. Next, we're going to move on to the outlet. So if we press on outlet, we can see that the type is a pressure outlet, so that is good. If we double click on outlet, it will open up the window that we need. And here we need to specify our static pressure and static temperature at the outlet of our nozzle for the subsonic flow condition. And again, these were found through pressure and area ratios, the calculations of which I showed earlier on in this video. So our gauge pressure, this is the static pressure at the outlet, and this was found to be 237,545 pascals. and the static temperature was found to be 207.35. She didn't show you guys how to find this temperature since it's not the same as your total temperature, but it is found the exact same way as finding your static pressure at the outlet of the nozzle. So with these conditions in place, I can go ahead and press apply and close this window. Now with our boundary conditions in place, we can go ahead and move on to the solution portion of this analysis. If we double click on methods just to verify them, these are looking good. We do not need to change anything. We do want implicit formulation and second order upwind, which should be defaults when you run Fluent, so that is good. Next, for our monitors, if we go ahead and press on the plus beside monitors and double click on residuals, we can see what our convergence criteria is. So when the analysis is being run, the accuracy of our result is based on the convergence criteria that we have here. Now, this is a fairly good criteria, but since this is a very simple analysis that does not require a lot of computational power, I'm going to go ahead and try for an even better convergence criteria just to get a better result. So I'm going to go ahead and change all of these to 1e to the -6. Press OK to confirm the changes. And so now finally, what we want to do is initialize the calculations. So I'll go ahead and press on initialization. And we'll just do a hybrid initialization. So click on hybrid initialization and press initialize. And as you can see, that is very quick. Down in the console window below, it says hybrid initialization is done. So that is good to go. The last thing to do now is to actually run our calculation. So we'll go ahead and press on run calculation. And so the only thing that we're going to want to specify here is the number of iterations that I want to run my calculation for. Now we are going for a 1e to the -6 convergence criteria. So we are going to have to run more iterations, but that is okay, because again, this simulation does not take up a lot of computational power. So I'm going to try to run this for 4,500 iterations to see if I get any convergence. So with all that being said, I'll go ahead and press on calculate. And as you can see here, it's starting to write the calculations down to the console window. And we have a progress bar here that shows us our percentage left in our analysis. And we also see how many iterations that we have left to go. And it's also printing out our residuals to the screen. So this is going to take a bit of time. So I'll go ahead and let this run, and I will catch back to you guys in a little bit. Hey guys, welcome back. We can see that the calculations have been completed. So we can go ahead and move on to the post-processing, viewing some contours and some graphs that may be of use to see what happened in our converging diverging nozzle. So I'll go ahead and press on OK. And so the first thing that we're going to do is build a contour. So to do this, I'm going to go down to results and press on the plus beside graphics. And I'm going to double click on contours. Now, the first thing that we're going to make a contour of is the Mach number in the nozzle. So this is a contour of velocity, since the Mach number is a velocity ratio. And down here, we're going to choose Mach number. And we'll go ahead and press on save and display. If we close this window, we can see this is the contour for the Mach number in our nozzle. Now, this is only half of the full picture. So if we wanted to see our full nozzle, we'll go ahead and press on view. And in the category views here, press on that. And for mirror planes, we're going to press symmetry, because the symmetry line is the mirror line. So press on symmetry and press apply. And now we can see our whole nozzle is appearing based on the results from the top being mirrored over the axis of symmetry. So we'll go ahead and close this window. And as you can see, we got fairly good results. As I mentioned at the beginning of the video, the parameters that we initialized at the outlet was for subsonic flow, meaning that our flow would increase in speed in the converging part of a nozzle. But since it did not quite reach a Mach number of 1, because the pressure back here is too high, the flow will remain subsonic and decrease in velocity as it goes through the diverging part of the nozzle. The other thing that we can do is create a plot for the Mach number along the center line of our nozzle. So we'll go ahead and for that, we'll press on the plus beside plots. We'll actually double click on plots and we'll double click on XY plot here. So this is going to create a new plot. Now, as our y-axis function, we're going to want to choose the Mach number. So to do this, we need to choose velocity and then choose Mach number in this drop-down menu. And we're plotting this as a function of a direction vector. The direction vector being the axis of symmetry, since this is located at the center of our nozzle. Make sure that the plot direction is 1 in the X, 0 in the Y. So now we can go ahead and press on plot. And it will plot to screen the Mach number as a function of the position along the center line of our nozzle. And this graph sort of shows the same picture that we saw during the contour. As we move through the converging part of the nozzle, our flow accelerates. And since it does not reach a sonic speed by the throat of the nozzle, the flow remains subsonic. And so it decreases in speed as it moves towards the exit. So there you have it. Now, other plots that may be of interest to look at are your static temperature and pressure. So we can go ahead and look at those as well. To do this, our y-axis function is pressure. And here we're going to choose static pressure. So that is good. And the rest of the information is going to be the same. So we can go ahead and plot that. And we can see the static pressure relationship in the nozzle. We can see that the static pressure, as it moves through the converging part of the nozzle, begins to decrease as the speed of the fluid increases. And since the pressure at the exit of the nozzle is too high, the pressure at the throat never reaches sonic flow, as I mentioned before. So your flow is going to remain subsonic. And as a result, as it moves through the diverging part of the nozzle, your speed's going to decrease. And as a result, your pressure is going to increase. Now, if the flow were to reach sonic speeds at the throat, which we will see in the next video, it is expected that your static pressure would continue to decrease as your speed would increase supersonically. But again, that is for video number 2 in this series. And finally, we can also go ahead and check the temperature, the static temperature, as a function of the position along the center line. And it shows a very similar story to the one that we saw for static pressure. And so there you have it. Those are all of our graphical relations along the center line of our nozzle. Make sure that you save this graph if you need to, or if you want to copy it to clipboard, very easy to do, to enter into, say, a report that you need to generate. You could go ahead and press on the icon here, copy screenshot of active window to clipboard. So essentially what it's going to do is take a screenshot of the window you have active here. So say if you had the scale residuals active and you pressed on this icon, it would take a screenshot of your residuals. So if you want your plot, make sure that this is active. press on this button, and you can see that down in the window below, it says copied screenshot of active window to clipboard. So you can go ahead and copy paste that into a report. And finally, one last note, you can also create more contours for your other parameters. We made it for the mock number. You could go ahead and make it for static pressure and static temperature in order to have a colorful representation of them. So to do that, you just create a new one, and you can even name it what you want to make sure you don't get confused. So you can name this pressure, and we would call this pressure. Come on, call this pressure, static pressure. So that is good. Just save and display. So this is the colorful representation of our static pressure in the nozzle. Now, unfortunately, you do need to close this window and create a new contour if you want to make your temperature one. So close the window, make a new one, name this temperature, and choose your static temperature to get colorful representation of it. And there you have it. That is how to set up the analysis for a converging diverging nozzle in ANSYS Fluent, specifically for subsonic flow conditions. In the next video, we're going to go through the calculations of supersonic flow conditions. And we will go back through the setup of the analysis to get supersonic flow results for our converging diverging nozzle. So I hope you guys enjoyed the video. Don't forget to like the video if you guys thought it was helpful, and subscribe for more engineering content.